record. So if you consider the constant pressure process, this is isobaric. Isobaric is constant pressure. So what happens is the heat which you are giving, part of the heat is given for work done, and only the remaining is used for delta U. Okay. So to raise it to the same temperature, right, you have to give more Q because some of the energy will be gone to the work done. And that's what we are going to study here. So specific capacities at constant volume process and constant pressure process. Okay. And if you're wondering what is specific capacity, right? We studied Q is equal to mc delta T in the previous chapter. So C is the specific capacity. So Q divided by m delta T. So we already studied this. So that means how much energy you have to supply for a given kg, for given 1 kg of substance to raise it by 1 degree Celsius or 1 degree Kelvin, 1 Kelvin. That's the meaning of specific capacity. But now what I'm saying is there are two processes. One is constant volume process. Then there is something called constant pressure process. So constant volume process we call it as CV. Here we call it as CP. So this for constant volume process, I already showed you the diagrams. So nothing wrong if you take it down one more time. So constant volume process means you put a piston here and then don't forget to put a stopper here. Okay. So when you put a stopper here, the piston does not move, even though you have a rod here. It doesn't go up. Why? Because it is going to be stopped here. As you heat it up, it will not go beyond the stopper. That means change in volume delta V is equal to 0. That means work done is equal to P into delta V, which means delta V is equal to 0 means work done is 0 because piston is not moving. Which means Q minus W is equal to delta U. So work done is 0, which means Q is equal to delta U. This is what we saw for constant volume process. Okay. Again, I'm not talking about constant pressure process. I'm talking about constant volume process. So instead of Q, sometimes we write it as delta Q. So delta Q is equal to delta U. If I divide by delta T on both sides, the value does not change. And if you go back to your basics, Q is equal to mc delta T. So if I take this as delta Q by delta T is nothing but m into C. Now that we are talking about constant volume process, you can write as CV. Either you can talk in terms of mass, or you can also talk in terms of moles, number of moles. Okay. So listen carefully. We talked about specific capacity, or we also talked about molar specific capacity. So the same formula can also be written as delta Q is equal to number of moles into CV. But then this CV I take it as specific capacity. This CV, small CV, we take it as molar specific capacity. Okay, so unfortunately, different books will confuse you. Okay, so if you put a mass here, it is specific capacity. So take it down properly. Because you have mass here, meaning this is joule per kg per Kelvin or Celsius. But if you put number of moles, then this has to be molar specific capacity. Which means joule per, instead of kg, it is joule per mole per Kelvin. That's all. So that's the difference. So only then, you know, the mole and mole will cancel. Here the kg and kg will cancel. Okay, temperature and temperature will cancel, and what I will get is delta Q, which is joules. Again, different books will call this by different names. Okay, don't get confused. As long as you understand the concept, you should understand that, you know, this is molar specific capacity and this is specific capacity, mass specific capacity. In the handbook, I am using capital means mass, small c means mole. So having said that, when I bring the delta T in the bottom, so bring the delta T on this side. So delta Q by delta T can be written as mu into CV. So try to write a little bit small so that, you know, this CV represents the molar specific capacity. So coming back to this formula, delta Q by delta T can be written as mu into CV, which is nothing but your delta U by delta T. So what this means is the change in internal energy for a corresponding change in temperature is given by mu into CV. So very often we are going to use this formula. So keep this as a ready formula. If this is confusing, very simple. Bring the delta T on this side. So you know that Q is equal to MC delta T on mu into CV delta T. So we studied that W becomes 0, which means Q and U are same, which means in place of Q, I can put delta U. That's all. Okay, if this is confusing, you can write the same equation like this. Anybody not following anything, please raise your doubts immediately. Okay, not an easy one. If something is not clear, please ask. So how did you get this step? You know, what is this? What is that? Anything not clear? Okay. So once you understand this one, constant pressure process is also very simple. So the Q which I am supplying, some will be lost in, some will be gone in the work done. Only the remaining will be used for heating up the gas. Which is your delta U, internal energy increase. So you know that W is equal to pressure into delta V. Okay, very first definition we study. So Q minus W is equal to delta U. So Q minus P delta V is equal to delta U. So Q is equal to P dot delta V plus delta U. If I, again, as I told you in the previous one, generally we like to show it like, delta Q. If I divide by delta T everywhere, delta Q by delta T, then I have to divide by delta T here also, which means delta T here and delta T here, so that the value does not change. But remember, we are talking about constant pressure process. It's not a constant volume process. Okay. So I can say Q is equal to mCp delta T. Okay. Because we are talking about constant pressure. Or you can say Q is equal to mu into small cp into delta T. Why? Because if I want to write in terms of moles, then I will write as mu into Cp. So if I bring the delta T on this side, Q by delta T will become mu into Cp. This one from the previous derivation, delta U by delta T, we found it as mu into Cv. So I'm going to apply it over there. Even though it is coming from constant volume process, what it means is it has got two elements. One is for the heat energy increase alone, and the another part is to increase the work done. Okay. So this one you can write as mu into Cv. Anybody not following this step? Go back and check the previous one. Okay. This one, if you remember the ideal gas equation, you know that PV is equal to mu RT. Okay. If I differentiate it on both sides, keeping the pressure constant, remember we are talking about constant pressure process, which means pressure is same, but the volume is changing. Number of moles is not going to change inside the cylinder. R is a constant, but the temperature will change. So if I bring the delta T on this side, mu into R. That's my side derivation here. So again, as I always say, this is my main derivation. Okay. And all these things are side notes. Okay. So if you confuse the main derivation with the side notes, obviously you will not be able to remember any of the important derivations. So you see the mu is same everywhere. So I can bring the Cv on this side. So it will become Cp minus Cv is equal to mu into R. So mu I can cancel it everywhere. So what is remaining is Cp minus Cv is equal to R. So that's a very important relationship. Okay. This is universal gas constant. This is molar specific heat capacity for constant pressure, molar specific capacity for constant volume. whenever you see the R is the unit for R is joule per mole per Kelvin. Okay, which means to say that it is always in terms of moles. Okay, the kg does not come here. So this relationship is called Mayer's relationship. I think it must be the name of the scientist. Mayer's relationship. Who found this or derived it? Any question, any doubts, anything confusing? Veer, are you following everything?
Yes, sir.
Okay. The recent days, I don't see any participation. Okay. I don't know if you are following everything or not. What about you, Kirtan?
Yes, sir.
Also following everything?
Yes, sir.
Can anyone tell me if you understood all these things, you should be able to answer this. So which one do you think will be having higher value, CP or CV? Hmm? The energy which you are giving in constant volume processes completely used for only for heat energy increase, right? The internal energy increase. Whereas in the case of constant pressure process, some of the energy is gone for work and only the remaining is available for heat energy increase. So in the case of constant pressure process, to raise the temperature to the same value, right, you have to give more work, more energy. Even look at this equation. Cp, so if you write this properly, Cp is equal to R plus Cv, or you can say Cv plus R. Cv plus R. So what does that mean? It means that this is a positive value, this is a positive value, so definitely Cp has to be higher. Any questions, any doubts? So Kirtan, you said Cv is higher, but actually Cp is higher. Are you able to follow? Okay. I'll show you where it is in the handbook. Okay, so whatever I derived, everything is given here. I may have skipped some of the steps here. Okay. So if you have your class notes properly, I think it will make sense. Okay, then let's talk about quasi-static process and non-quasi-static process. Quasi means something like almost. Okay, the static process means the values are not changing. So it's a very simple concept. Okay, so it's a theoretical way of we are trying to make a practical thing into a steady state theoretical situation. Okay, so what do you mean by that? It means suppose if you take a piston like this, let's say I have a very thin metal sheets, very thin uniformly designed metal sheets, so I can remove one sheet at a time. Let's say I have a stopper here. Okay, so this is one situation. So you have some pressure, volume, temperature here, right? Suppose if I remove one sheet at a time, what will happen? Will this piston move up or not? If I remove this weight, one sheet at a time. Will this piston move up or not? Very good response. Nobody can answer it.
Down. It will move down.
It will move down. If you remove weight, will the piston move down or will it move up?
If you move the weight, it will go up. It will go up.
It will go up, right? Because if you're removing the weight. Okay. So in another situation, imagine that I have the same gas and same piston, same pressure and volume temperature. But now instead of having this thin metal sheets, I have one single block, something like say 10 kg. Okay, so same stopper here. So what happens is, what I'm trying to say here is, if I remove this 10 kg, what will happen is the weight is removed, which means this gas will try to push it upwards, because right now it might be very compressed. The moment I remove this, it can go up, okay, because this pressure will push it up. But this will happen very quickly, okay, because there is a huge difference. Suppose if you had a pressure, volume, temperature at this point, right? Let's say it's coming over here. Listen carefully. After the moment I remove this, this piston will come and hit over here, and I will be able to measure the pressure over here. So I'll say P2, V2, T2. But then I cannot tell exactly, what is the path it followed. Okay, I cannot tell whether the pressure was here at a particular instant, or whether it was here, or whether it was here. There is no way I can tell that. Okay, just for theoretically speaking, just for a convenience, we can show some dotted line like this. In reality, I cannot tell where it was, that microseconds or nanoseconds. I cannot really tell, what was the pressure and temperature. Okay. However, if I come to this side, if you take the pressure here and volume here, if you had P1, V1, T1 here, okay, the moment I remove this one sheet at a time, right, maybe this pressure will slightly decrease. So I can tell what is the value here. The moment I remove the second sheet, maybe it will come back and stop here. Okay, the pressure will stabilize here. You see here that there is a continuous turbulent motion. The moment I remove this, there is a huge motion here. But here I'm just removing very, very small. Okay, it's called in science or in mathematics, we call it as infinitely small. Or infinitesimal. Okay. Meaning it's very, very small at a time. Okay, so when I do that, what will happen is there is no sudden changes. So what happens is the pressure and volume and temperature will stabilize very quickly, and slowly it will come down like this. So the final point will be almost close to this. Okay, in this case, right, since there was a sudden change here, there'll be some heat losses, whereas here there is no sudden change here. Okay, which means the losses will be less here. So since I know, I'm able to tell what is the pressure here, what is the pressure here, what is the pressure here at every location, every volume, right? Even in that nanoseconds, right? This we call it as quasi-static process because it's almost static. This one is called non-quasi-static process. So most of our day-to-day life processes are like this. This is more like an ideal situation. So this is day-to-day. Engine, pressure cooker, all these things. It's a non-quasi-static. Whereas quasi-static is more like an ideal situation. Okay. But still, we study this ideal situation because, we can do a lot of, theoretical work and derive some important relationships. So let me say this one more time. These points here are real points. Actually, the pressure was here, the volume was here. Okay, but these points are not real points. We are just assuming that. Okay, only this and this are real. So only initial and final are known. Here, in addition to initial and final, in between points are also known. When I say points or states, right, this is state. Known means we are talking about the pressure, volume, temperature values. Any questions? If they ask you what is quasi-static and what is non-quasi-static, will you be able to explain based on this? Okay, of course, drawing is a language of engineers. Okay, you can write 10 different paragraphs. Okay, but if you draw a simple diagram like this, it will make more sense. Of course, you have to write the paragraph. I'm not saying you don't have to write it, but drawings are much more, it conveys the message much more easily. So if I'm trying to explain a child how an elephant looks like, okay, I can say it's going to have a very big legs, it's going to have a long tail, it's going to have a big stomach, and then there is a huge trunk. So I can keep on talking. But or another method is simply draw a simple diagram like this. Okay, so that's how elephant looks like. Okay, that will make more sense than talking about that. So that's what I try, keep saying that drawing is the language of engineers and scientists. Okay, what else can I talk about? Okay, I forgot to say, okay, I can open the handbook here. So look at this. Each point or state of the process is in thermodynamic equilibrium, meaning P, what is the meaning of thermodynamic equilibrium? Pressure, volume, temperature are well defined. W is made up of very small weights, dW, which is removed in succession gradually. So one sheet at a time. It is a very slow process. Here the opposite. Okay, so that's why I told you studying this chapter is very, very easy if you, try to, contrast these two different things and then study them. It's very, very easy. In the textbook, everything is going to be given one below the other. Okay, of course, you have to read through the textbook, but here I'm saying in the handbook, you can read it much more easily. So in your scientific papers, right, in scientific documentation, when you put a into mark like this, it means you did an experiment and you found a value there. If you simply show a dotted line, it means you did not do any experiment. You are just guessing that the line might be somewhere here. That's the meaning of this dotted line and this points. Okay. So if you are not done the experiment, then you should not show the points. Okay. You should show only the dotted lines like this. So usually this is a reversible process. This is a non-reversible process. Why? Because if I start if I start putting back, one sheet at a time, slowly what will happen is it will come back to the same position. Same pressure and temperature will be achieved. But here, if I put back the same weight, right, it may not be achieving the same pressure, volume, and temperature. The reason for that is this was a slow process, which means the friction was very less here. Okay, friction, viscosity, all those dissipative effects. Okay, so we call it as dissipative effect. Okay, let me make it a little bit bigger. So these kind of dissipative effects such as friction, viscosity will be less here. Yeah. Whereas here it will be very, very high. So because of that, there will be some heat losses. So coming back to the same point may not be possible. So it is hypothetical, meaning it's more like a theoretical. Whereas in reality, this is what will happen, more practical process or irreversible process. Anybody having any doubts? Are you clear with this quasi-static and non-quasi, reversible and irreversible? Ashwant, no doubts?
So no.
No, sir.
Okay, very good. Kevin?
Sir, no, sir.
Okay. Uzma is being quiet today. What happened? Everything
No,
following?
sir.
No
Yes, I'm
doubts?
following. No doubt, sir.
Okay. Samyukta?
No doubt, sir.
Okay. Again, I'm going very slow. Okay, it's your responsibility to clarify any doubts you may have. Okay, let's see. In my opinion, okay, for your school exams, I'm trying to teach everything. Okay, so for your school exams, if your school teacher has skipped some of the topics, maybe you can skip those things and study only those things for your school exams. Again, for your entrance exam, pretty much you have to study everything. Okay, if you're skipping it, obviously you are not preparing for any entrances at all. And joining, all of you will be very enthusiastic. And after 2 weeks, slowly the enthusiasm keeps coming down. And before the exam, again, it will slightly rise up. And again, it will start coming down. Okay. Sir, I'm going to study for JEE, I'm going to study for NEET, this, that. And then after 2 weeks, sir, there is record work, this work, that work. So I'm not doing any numericals. Okay, so this is what I see with students. And only when you have some, long-term goal, only when you're working hard, you'll be able to do it be able to prepare for entrance exams. Okay. Okay, again, I will leave it to you. So, because there is a saying in English, excellence is always optional. Okay. So nobody is going to compel you to excel. So if you want to excel, it is your own decision. Okay. What else can we talk about here? First law of thermodynamics applied to isobaric process. Okay. Maybe I can take the picture of this and explain it a little bit easily. Or let's do a little bit of mathematics here. Okay, and then we'll come back to this. Take it down, very important derivation. Work done by isothermal process. Okay, so it's a derivation. Already know what is isothermal process, so I don't have to explain it. Q minus W is equal to delta U. Isothermal means same temperature. Same temperature means internal energy does not change. So it means delta U becomes 0. So Q is equal to W. Okay. But W is nothing but we define W as integral of P dot del V. Why? Because if I'm integrating from V1 to V2, we said it is the area under the curve. I may not have given the diagrams, so take it down properly. Which means at every point the pressure changes. So that means I have to integrate it from to find the area. Just like I said in the previous thing, PV is equal to mu RT from the ideal gas equation. Okay. So I have P delta V. So that means if I differentiate this dV, again, this differentiation might be confusing. It's not given in your handbook also. So take it down properly. As I always say, there is a huge flaw in the educational system. Okay. You have not been taught with differentiation or integration. Okay. Or at least most of you. Maybe the ISC students, I think you have a little bit of integration differentiation knowledge. So I keep the P as such and I have to differentiate dV. Plus I have to keep the V as such and I have to differentiate the dP. Okay. But that is for a different process. Mu RT dV dP by D. Okay. So mu RT. So you know that we are talking about isothermal process. So that means the temperature is constant, R is constant, mu is constant. Okay. So which means if I differentiate this, it will become 0 because it's a constant value. I think this derivation is not required here. Mu RT divided by dV P by V. Okay. Okay, this is not required here for this derivation. I simply want P. So P can be written as P is equal to mu RT divided by V. So in place of P, I'm going to write as mu RT divided by V. So mu RT, as I told you, we are talking about isothermal process, which means temperature is constant. Mu is number of moles constant, R is universal gas constant. So mu RT is a constant, so keep it outside. Integral of dV by V. This will become ln V. This is again coming in your mathematics. Okay, so ln X differentiation. If I differentiate ln X, I'll be getting 1 by X. If I take this dx on this side, I'll be getting dx by X. Differentiation of ln X. So just like square root goes on the other side to become square, or square becomes square root, this differentiation, when I take it on the other side, it will become integration. So for now, you just have to believe whatever I'm saying. So take it down because you don't have any other choice. So it means integral of, take it down properly. So integral of dv by v can be written as ln v. Then you have to apply the limits, lower limit, upper limit. So of course mu rt is a constant. Ln v2 minus ln v1. But in your mathematics for log, right, you must have studied a formula. Log m into n can be written as log m. Anybody? Log? Nobody knows this.
Yes, sir.
Log mn can be written as log m plus log n. Similarly, log m by n can be written as, any guesses?
Log m minus log n.
Okay, very good. So some of you are still awake. Okay. So what this means is, my maths teacher used to teach me log is something like a different world. So anything which you want to do multiplication here in our real world, if you take it to the log world, you can do addition. Of course, in your chemistry, when you bring it back, you have to do anti-logarithm, right? So when you take it to the log world, you can add them. And after adding it again, when you bring it to the real world, you have to do anti-logarithm. Again, I'm not going to talk about the anti-logarithm right now. So similarly, something which you want to do like division in this world, when you take it to the log world, you can do subtraction. So that's the reason why we use logarithmic tables. Okay, at least nowadays we are using calculators and computers. In olden days, scientists and engineers, they did not have any other choice, so they had to use this log method. Which means to say log v2 minus ln v2 by ln v1, right, can be written as ln v2 by 1. Anybody wondering why I'm not writing it as log, instead I'm writing as ln? What does that mean? No answers, which means nobody knows. You see, a lot of mathematics is missing, so take it down. If I write log base 10, it's called common logarithms. I think this is what you will be using mostly in your chemistry data table calculations. But if you put log base e, right, then it's called natural logarithm. So this, in their calculators, they will show it as n. N stands for natural logarithm. Okay. Sometimes in the calculator, you will see LG. LG stands for common logarithm. Ln stands for natural logarithm. In your textbooks also, we use the same method. Ln means natural logarithm. Remember, we are talking about constant temperature process. Okay. What do you mean by that? Constant temperature means PV is equal to mu RT. So this is constant because T is constant. So PV is equal to constant. What does that mean? It's called the Boyles Law. Okay, we already talked about this. As pressure increases, volume decreases. Okay. So pressure P1 V1 is equal to P2 V2. So if I want V2 by V1, I can write this as P1 by P2. So this is a side derivation. You see, there are so many side information you need to know to do this simple derivation. So V2 by V1, I'm going to write as P1 by P2. So mu RT ln P1 by P2. That's all. So this is one formula. Remember, we are talking about work done. 1 to 2. So this is one formula, this is another formula. So if this is in volume, then you can use this formula. If it is in pressure, you can use this formula. So let me zoom out. So please take down all these things. Okay. Again, as I always say, if you're lazy enough, lazy to take down the notes, then you're going to suffer. So I warned you many times. Any questions? Anybody still copying? Can I change the screen?
1 minute, sir.
1 minute, sir.
No.
Yes, sir. Done.
Okay. Anybody else copying? Can I change? Okay. So what we did right now was work done by isothermal process. So similarly, we are going to do work done by adiabatic process. So you already know what is adiabatic. Adiabatic means a dia. So dia means through. So heat can pass through. A dia means it cannot pass through. Okay, adiabatic process. Which means to say that the Q becomes 0. Right? So in adiabatic process, right, there is a important formula called PV power gamma is equal to constant. Either you can write as constant or K. This gamma, right, is what is called Cp by Cv, ratio of specific capacities. So take it down, gamma is nothing but the ratio of specific heat capacity. Cp by Cv. Okay, as I told you, Cp is bigger, Cv value will be smaller. Okay, which means gamma will be always greater than 1. This we are taking it without proof. Okay, so for now, it's out of scope of the textbook right now, so we don't care about the derivation for this. So what we are more interested right now is work done for this process. So which means we start with the same formula which we studied earlier, P dV, integral of P dV. So we have to integrate it from V1 to V2. The diagram is pretty much going to be the same. Okay. Only thing isothermal means we will show something like this. Adiabatic means it will be shown something like this. So this is isothermal. Okay, adiabatic means it will be a little bit lower. Always taking down the diagram is much more, interesting to understand, what we are talking about here. So I want P. So V power gamma, I'm going to bring it on the side. So that means in place of P, I'm going to write as K divided by V power gamma. Then dV. This is integral V1, V2. Constant can be kept outside. dV by V power gamma. V power gamma can be written as, this can be written as V power minus gamma. You know that the simple formula integral of x power n dot dx is equal to x power n plus 1 divided by n plus 1. Okay. So that means, of course, we'll put a c here plus constant. Okay. So v power minus gamma. So this value plus 1. So it means v power minus gamma plus 1 divided by minus gamma plus 1. Very simple, but because of the powers, it may look a little bit complicated. But you should have the understanding. If you have a good understanding, you will not get scared by these things. So this I can write as 1 minus gamma minus 1. I'm going to keep this outside because it's a constant. So minus gamma plus 1, so that it doesn't disturb me in this process of substituting the C1 and V2. Remember, one is V, the other one is gamma. Okay, both are different. So when I take this to the bottom, right, this powers will change the signs. So that means minus gamma will become plus gamma, plus 1 will become. So it's something like this. 1 by 2 can be written as 2 power minus 1. 1 by 2 power 3 can be written as 2 power minus 3. Okay. That means when you take it to the top, this will become minus. So similarly, when you bring it to the bottom, this I have to multiply by minus 1. You see, I'm just trying to write each and every step so that you don't miss anything. This I haven't already integrated it, so I'm not supposed to write dv. So I made a mistake here. So if any step is not making sense, please stop me. Now I have to do upper limit minus lower limit. Here we are going to do a small adjustment. Okay. So I know that PV power gamma is equal to constant. So when I bring this constant over here, I can write this as I'm just multiplying the K instead. So this can also be written as P1 V1 power gamma is equal to P2 V2 power gamma. So that's the meaning of this constant. So when you go from state 1 to state 2, this relationship remains the same. So pressure will change, volume will change. But if you calculate the P1 V1 per gamma, that value will be matching with the P2 V2 per gamma. That's the meaning of this. I mean, you don't have to worry about these things. These are all the previous ones. So in place of K, right, I'm going to substitute this as, in place for this V2, I'm going to substitute this value, and for V1, I'm going to substitute this value, okay, because this is also equal to K. So in place of V2, I'm going to put V2, V2, V2 power gamma, V2 power gamma minus 1, minus P1, V1 power gamma divided by V1 power gamma minus 1. This might be slightly confusing, so please take a look at it. I'm just saying that this is equal to this, which happens to be equal to the constant value. So just to make it easy for me to cancel this out, here I'll be writing in terms of P2 V2. Here I'll write it in terms of P1 V1. That's all. Anybody not following means please stop me. I'm going to cancel this on this. So this is 1 power less than this. Okay. This is like, x power 5 and this is x power 4, which means I'll be getting x. Same thing here. So it means I'm going to write this as P2 V2 minus P1 V1 divided by minus gamma plus 1. But I told you gamma is greater than 1. So that means we like to write this as 1 minus gamma plus 1. So it will be like, gamma minus 1 would be better. So that means what we do is we interchange this. So when I interchange this, I'll be getting a minus. That minus, if I put it over here, I'll be getting 1 minus 1. Just a sec. Just a minute, I'll be back in a second. I will Okay, so everyone following this? Here I'm interchanging this, so I can interchange in the denominator also. That's all. So that's the important formula for work done of adiabatic process. This can also be written as, from your ideal gas equation, you know that PV is equal to mu RT. Remember, this equation is applicable for adiabatic also. Okay. Of course, I have given you one more equation, which is adiabatic process. At the very beginning, I showed you this. So this is a characteristic equation of adiabatic process. Okay. But the ideal gas equation is also applicable. So PV is equal to mu RT is also correct. So that means P1 V1 can be written as mu R T1. So this can also be written as mu R is taken commonly out. So that means it will be T1 minus T2 divided by, remember it looks like V, it's gamma. So make sure you write it properly. So they will ask you to derive this work done by adiabatic process. Okay. So again, it may look like a lot of steps. The reason for that is, as I always tell you, you should know each and every step. Okay. But when you are doing it, you don't have to write all these steps. Okay. You can skip some of the steps. So maybe from here to here, you can skip, 2 or 3 steps. You can skip easily. So take it down properly. Any step which is not clear, please clarify immediately. Anybody still copying? Can I change the screen, or anybody copying? No answers. Okay. Okay, which means I'm going to assume that all of you have copied it. Okay, what else can I teach here today? I'm going to give you a quick introduction. Okay, so we finish these two things today. Again, you see, I just given only hints here. I may not have given you all the steps. So that's why I keep on saying don't depend upon the handbook alone. So take down your notes properly. So we are going to apply the first law of thermodynamics for two important processes which we already know. One is freezing, like water to ice. Another one is water to gas, like steam, vaporization. So both are isobaric process. What do you mean by that? When you are heating up, right? Let's say you keep a bowl of water when you are heating it up, which means you are not, the steam is kind of going out. Okay, so it's working against the atmospheric pressure. So what do you mean by that? Let's say I have some water here and you have some atmospheric pressure here. Okay. So as you heat this water, what is actually happening here is these water molecules are slowly getting converted to gaseous molecule, and that gaseous molecule, right? So let's say I'm showing this water in yellow color. So the water molecules are going to become steam and they're going to press against this air molecules. Okay. So it means The air pressure is what is acting above this. Or you can say atmospheric pressure. So it means always there is some atmospheric pressure. So this vaporization is happening at a constant pressure. That's why we call it as isobaric process. Okay, so we are pushing this steam against, or you can say water molecules. So it's pushing against this air molecules. Okay, so read this with that background. Volume of liquid expands against the constant atmospheric pressure. What do you mean by that? So this much water, if I try to hold the steam, what will happen is it would have expanded some 1,000 times bigger. Okay, so that's a very interesting fact that if you try to convert the water to steam, it will be like I don't remember was it 100 times or 1,000 times. I think it's 1,000 times bigger. Okay, so really huge difference. So the volume will be really big. The same amount of water molecules, but then it's kind of moving around. So it occupies more space. Some energy is used to do work against the atmospheric pressure, and most energy is used to increase the potential energy of the molecules by pulling them apart. Okay, so the water molecules are kind of pulled apart from each other. So during phase change process, the kinetic energy is not changed, only potential energy is increased. So something like pulling your rubber band. So in that time, the energy is used to pull the molecules apart. It's not used to push the molecules with higher speed. So that's what we studied at the very beginning of this chapter. Okay, internal energy consists of potential energy and kinetic energy. But whenever you're increasing the temperature, you are talking about more faster molecules, which means kinetic energy. But if you're converting from water to steam or ice to water, then you are pulling the molecules apart, which means it is potential energy. So during the vaporization process, the temperature does not change. So that's why I said here, increasing the internal energy here. During phase change process, the kinetic energy is not changed. Only potential energy is increased. Okay. So this you have to remember the concept which we studied here. So anybody remember the name of this curve? Nobody remembers? Wow. I thought you even wrote a test on this. Nobody remembers? What is this curve? What does it represent? Anything? Here it is melting process. Here it is vaporization process. Okay, let me quickly complete this. So Q is equal to W plus delta U from the isobaric process. Go back and check. This is the formula we got. Okay, so Q is equal to, I told you in this slanting line you can use MC delta T. But in straight lines you have to use M into LV, latent heat of vaporization. So Q is equal to M into LV. Change in volume is volume of gas minus volume of liquid. Okay, so this is gas minus liquid. Delta U remains the same, that's all. Same thing is applicable here, so do it as a homework. Okay. Only thing, instead of gas and liquid, it will be solid and liquid. Okay. since you are taking the heat away, right? So here you are giving heat, here you are removing the heat. So that's why you get a minus. So giving heat means I told you it is positive. Removing heat from object means it is negative. Okay, so take it down. So take it as a homework. So your homework is to study all the topics which you have covered so far. Okay. So most probably, I think, this is over. So the one last thing which is remaining is Carnot engine. Okay, a bit confusing. But this derivation is not difficult. Okay, it's easy only. So after this class, you may have to, we'll get started with some numerical. You can get started with the numericals now itself. You can try some of the problems. Any announcements of the final exam dates for you?
No, sir, as of now, nothing.
Nothing. Okay. Okay, let us not worry about that right now. Okay, again, I'm going a little bit slow so that you will be able to follow everything properly. Okay, I'm going to stop here. Yeah.
So for us, our school announced is February 16th. Sir.
February 16. Yours is your birthday, is that right?
Yes, sir. Your birthday.
Okay. February 16. Okay, around mid of the month. Okay, mid of February. Okay, that's what I think it will be true for other schools also. Which means to say that we have only approximately 2 or maybe 3 weeks maximum. Okay, as I said, every year I face this difficulty, okay, this challenge. Somewhere I have to, speed up a little bit. So maybe instead of doing kinetic theory of gases, I'll do oscillations and waves. Okay, so that is more important. And then we'll come back to kinetic theory of gases. Okay, thank you all. I'll stop here. If you have doubts, stay back. Thank you. Bye.
Thank you, sir. Bye, sir.
Thank you.
Thank you, sir.